Welcome! In this video, I will explain what the limit is. Let us consider an example. f of x equals x cubed minus 3x squared plus 3x minus 2 divided by 3 times x minus 2. You see that the function does not exist at x equals 2, because then we have to divide by 0. However, we can plug in numbers very close to 2. For example, at x equals 1.9, we have f of x equals 0.9. At x equals 1.99, we have f of x equals 0.99, and f of 1.999 equals 0.999, etc. It seems that if we take x closer and closer to 2, the value of f of x gets closer and closer to 1. This also happens if we plug in values of x greater than 2. f of 2.1 equals 1.1, f of 2.01 equals 1.01, and f of 2.001 equals 1.001. Indeed, if we draw the graph of this function, we see that it's just an ordinary graph with nothing special happening anywhere, except that we are not allowed to plug in x equals 2 into f. We indicate this in the graph by drawing an open circle at x equals 2. This seems kind of lame, and we should just be able to associate a value to f at x equals 2, the value suggested by the graph, which is 1. Formally, we say that the limit of f of x as x approaches 2 equals 1. Let's make this reasoning more precise. What we want is that for all x close to 2, the value of the function is close to 1, though we don't care about the value of f at x equals 2 itself, or even whether it exists at all. First, we have to specify what we mean by close to 1 and close to 2. For example, suppose we allow for a tolerance of 0.5. Then we want to show that the function values of f remain between 1 minus 0.5 and 1 plus 0.5 for x close to 2. Everything in this horizontal band is now considered to be close to 1. The graph also has a red part, which indicates that there are x values for which the function is too far away from 1, outside our chosen level of tolerance. But that's okay. We only want the function to be close to 1 for x values close to 2. Now we have to specify what we mean by close to 2. As a first attempt, we consider every x value in the blue vertical strip to be close to 2, while values outside this strip are considered far away. But as you can see, our strip is too wide. There's still a red part of the graph inside the strip. Remember that we want that the function value is close to 1 for all these x values. We can make the vertical strip smaller by moving the blue lines close to 2. And as the strip gets smaller, the red part of the graph in the strip gets shorter and shorter until at some point it is gone. With this adjusted notion of close to 2, we can say that for every x close to 2, the function value is close to 1, exactly as we want. Of course, we have now shown that for this particular notion of close to 1, a tolerance of 1/2, it is true that for all x close to 2, the function value is close to 1. But 1/2 is a pretty big tolerance. So we want to be able to do this for smaller tolerances as well. So what happens if we set the tolerance equal to 1/6? Then the horizontal band gets smaller, and a larger part of the graph will be outside this band. In particular, we see that our vertical strip is once again too wide, as it contains a red part of the graph. However, we can shrink the vertical strip to compensate, so that eventually, once again, only a green part of the graph is in the vertical strip. This corresponds to being more strict about saying which x's are close to 2. Now we can be precise about what we mean when we say that the limit of f of x as x goes to 2 equals 1. It means that for every tolerance you choose, any size of horizontal band, there is a vertical strip such that for every x in the vertical strip, the function value differs less than the tolerance from 1. Beware! Sometimes people say that the limit as x goes to 2 of f of x equals 1 means that however close to 1 you want to get, you can find x's close to 2 which get you there. However, this is much weaker than what limits actually mean. The point is that however close you want to get to 1, all x values sufficiently close to 2 get you there. In particular, for x close to 2, you cannot get values of your function far away from 1. If you want to use this definition to calculate a limit, you would have to precisely say how wide the vertical strip can be for each tolerance. This is an annoying task, so you typically don't want to do this. Fortunately, there are some tricks to calculate limits using much simpler techniques. Come to class to learn more.